We're going to talk about thermodynamic cycles, and what a cycle is it's a sequence of processes that begins and ends at the same state. Okay, so again, it goes one state to another state to another state, so on and so forth, eventually ending back up where it starts. Okay, so because of that, the change in properties over the course of the cycle it doesn't change. The beginning and the end are the same thing, so there's no change in properties, there's no change in energy. Therefore, from our first law equation, we can find that the work of the cycle actually equals the heat of the cycle. Okay, and again, that's because it begins and ends at the same point, so there's no change in energy over the course of one repetition of the cycle. Okay, so first type of cycle we want to talk about is a power cycle, in which we take some very hot source, okay, and use that heat to deliver work to the surroundings. So if you look at the figure here, we have a Qn, we convert that to some amount of work, and then dump heat to a cold body. So that natural motion of moving hot to cold, we get some work out of it. Okay, and we determine the performance by something called the thermal efficiency, and all of these performances are based on output over input, where my output here again is the work put out and the input is the heat put into it. So it's the work of the cycle over the heat into the system. Okay, now another way we can write this, again, because work of the cycle equals Q of the cycle, the work of the cycle can be Q in minus Q out. So we plug that in instead, and we get a little bit different form of that, just based on the heat transfers. So just a different way that we can write the same thermal efficiency. Now, this thermal efficiency has to be less than 100%. As we'll see, it's usually much greater than 100%. Usually 30-something percent is a pretty good, maybe 40% is a good efficiency for power cycles. Okay, and we'll talk much more about this when we get to the second law of thermodynamics. But for now, just know that we can't have an efficiency greater than 100%. Okay. The other type of system that we talk about are refrigeration and heat pump cycles. Now, it's two cycles, but the picture is identical for each cycle. And the idea behind these types of cycles is we get heat to move in the opposite direction. So instead of from hot to cold, we move heat from cold to hot. And the only way we can do that is by putting work into the system to move that heat in the wrong direction from what it would want to do. So from cold to hot. Okay. Now, one cycle that we use this for is a refrigeration cycle. And in a refrigeration cycle, the point is to cool space. So essentially, we're trying to control this cold region down at the bottom of the picture here. So again, our coefficient of performance is what we call this for refrigeration and heat pumps. Again, it's always output over input. So the output, what it is I'm trying to do is actually Q in. Okay, and that's Q into the system. That's the heat being pulled out of some surroundings. Okay, but it's Q into my system. So that coefficient of performance is Q in over the output, which is the work of the cycle. And again, I can write that in terms of just heats as shown there. So again, coefficient of performance is always output over input. For a refrigeration cycle, again, we're trying to cool down something, so we're pulling it out into our system. So it's Q in over the work input to the cycle. Okay, now heat pump cycle does exact opposite. Okay, it's the same picture as shown down here. It's just now we're trying to heat this space, so Q out is what's important, right? We're trying to keep some space warm. Okay, we're pulling, so it's like in a house, we're pulling cold from the outside and dumping it into the inside, which is backwards of how we think about heat moving, but we do that by putting work into the cycle. So coefficient performance here, again, is output over input, but the output for a heat pump cycle, even though it's the same picture, is Q out, okay, out of my system into the space over the work of the cycle. And again, I can write that in terms of just heat transfers as well. Now, this coefficient of performance for both refrigeration as well as heat pumps, we want it to be as large as possible, okay? And usually we're dealing with coefficient of performance of like 3 or something like that. But it can, it can get up, we're basically trying to get as large. It can't be infinity, but it's trying to be as large as possible. So that's how we deal with cycles. Just remember that all of these, thermal efficiency, coefficient performance is always the output that we're trying to achieve over the input that we're putting into the system.